Welcome back to another Medicinal Mass Media production. Today we have a fun little panel. We have Dan the Waterman, Jesse Patholite, and Beerman. And we're going to be going over something Beerman has found and written a paper about, total internal reflection. Dan the Waterman has done field tests with lasers about the curvature of the Earth and testing the Earth's atmosphere, and I believe Jesse Patholite has also done the same in the field. Welcome, guys. How are we doing today?
Good.
Yeah, good in yourself.
Thank you for coming. Dan, do you want to kick it off here?
Oh, I just want to thank you for giving us the forum, and we're trying to get more into science these days because we tend to argue about things most people haven't seen. And if they have seen, they don't understand. And in the past couple of years, I've had the pleasure to meet Beerman, and his inquisitive nature, neither being a flat earther or a glober, he's just a normie. He's just a regular person, not quite that normie. His mind works, and he ventures to understand where we live and why. And I think we all owe him a lot for that. So thanks for having us, Demon. It's important that we get these things sorted out. Jesse and I have also been talking for 2 or 3 years. None of us are contentious at all, and I believe we all have the same goals in mind.
Awesome. Does somebody want to present the paper in question, or maybe I can pull it up? I think I could try that. Give me a second here.
Yeah, I think you can pull it up. I will give a basic rundown of what it's all saying, but all the information will be in the paper. All the math is in the paper. But yeah, I'll give a basic rundown of what it's actually saying.
Let me jump a layman for everyone, because, for instance, Jeranism went out a couple of months ago and tried to do some stuff at Monterey Bay, and upon not being able to find his target, began scanning the coastline from his position and literally gave up, could not figure out what he was seeing. Literally couldn't figure out where the water line was, what a mirror line was, and how to decipher anything in the distance. It was very frustrating for him. I wish he was here today to listen to this. But what he said was, "I don't need your help." Like, okay, thanks. So that mirror line at the surface has been something Travis has been working on. What's Travis's YouTube name?
He's now the Ubercaster or something like that. He used to be the Plain Truth.
He's worked, he's put more hours than anyone into this in trying to identify what he used to call the ether band. And Beerman has taken that to the next level in analysis. So if we got it
okay,
up.
So maybe I got the paper pulled up here if everyone can see it.
Yeah, I got it open. I can see it.
Is this the time when I should just say
So maybe I should jump in straight ahead if you guys are up for that, just to give you guys the basic rundown of the paper, and then we can run through the paper of my findings at least, and how I came across this and why I wrote the paper. Should I start there on that side?
Absolutely.
Okay, great. So I was fascinated by looking at a sunset, and a few times looking at a sunrise, most of the time sunset. I live on the coast, and having a look at the sun, what it was doing weird things. It was peeling away, it was going in the opposite direction, and I just said, why is it doing this? And I wanted to get an understanding of why I am seeing what I am seeing. And then I was introduced to ships over the horizon, the inferior mirage, the Fata Morgana, and all sorts of phenomenon that we see on the horizon line. And no one could explicitly explain what is happening. They all speculated, this is what's happening, this is what we are seeing. And it just fascinated me that there was no distinctive answer. Even when I went to the schools, the universities, they could explain it, but couldn't show it to me on a smaller scale or explain it to me on different levels. So I said to myself, no, I got to try to figure this out for myself. So what I did is I've been looking into this for almost 6 years, and I had an epiphany, and I measured these temperatures at different levels in the air, and I realized that there's a a different index of refraction occurring within different temperatures within the air. And there's a standard one that you can use within science. There's one that you can say if you put in a temperature, there's a standard index of refraction for that temperature in standard atmosphere. So I started using that, using the actual tools to measure the exact index of refraction. But irrespective of that, that's why I'm asking for funding to help me get the exact amounts. But using the standard index of refraction for certain temperatures in the atmosphere, I came up with. Then I was looking at Snell's law, and I was having a look at how Snell's law actually works. When it hits a new medium, when it refracts and when it reflects, or what would cause it to refract and what would cause it to reflect. So then I said to myself, if I'm seeing an inverted image, that's telling me I'm seeing a reflection of something. I'm not seeing something refracted. But if I'm able to measure something with a solid pole, for instance, that doesn't bend, it's not going to bend through a medium. That pole is solid and it's not in the place that I'm seeing it. That is refraction. So I said, okay, wow, this is telling me there's a medium between the different indexes of refraction. And I said, is there a way to measure this? So I went to the universities. I asked these guys to help me with a mathematical calculation to measure where I would see where the critical angle would be, where I would see this refraction or reflection occur, where Snell's law would occur with these two different mediums. So months went on. I think it was about a year later. I eventually came up with the calculation that I have in my paper, which I was able to use to predict where I would see an inferior mirage occur. And my wife and I went out on 4 different days to confirm this. So I kept the Excel sheet, and we went out. We measured the temperatures just above the surface. It was 3 centimeters above the surface. Then we measured 1 meter above the surface. And I said to my wife, "Okay, this is the data we're going to use now, and let's see if this math works." So what I did is I put that data into the calculation. I actually developed a mirage distance calculator as well with the math built into it, which makes it easier that you don't have to do everything manually. So we went out and we took I made the prediction. My wife went out, we measured, told her to stop, and we rented out one of those construction workers' roller wheels to get the distance, and I used the P900 for measurement. So granted, yes, it's observation, but I told my wife to stop when I see her enter the inferior mirage. She gave me the distance, and we put that actual measured distance in versus the predicted distance, and we did this. I do have the Excel. I'll give it to you guys a little bit later, but I think we did 10 different measurements and predictions, and it's about 95% accurate each time in different days. So that's when I realized I'm onto something. This does not only work. Okay, the furthest I did was, I think it was 250 meters in my data sheets, but it also works closely. So I did even 5 meters, 20 meters. We did various distances. It worked every single time very, very, very accurately. Obviously, or not obviously, but I'm going to say yes, the closer the mirage was, easier to measure. It was a bit more accurate, probably because of observational measurements in this case. But every time I was able to predict this mirage, and I can still do it today. We can go out tomorrow. We can go out now. Okay, I can't go out now. It's dark on my side. You can go out. You can give me data. I will be able to tell you where you're going to see the inferior mirage. I'm confident I'm able to do it because have done it. I'm asking other people to do it as well. So I wrote a paper on my findings and how the inferior mirage, or why we are seeing inferior mirage, as well. This also works for a superior mirage. So it's not only inferior mirage, it's also a superior mirage, which would give the explanation of why we're seeing what we are seeing, specifically with the Fata Morgana. And the Morgana is like a an inferior mirage. We see the inverted reflection above the target, but we also see the refracted target above that. And this is all measurable. It's testable as long as you are able to give the of refraction of those current conditions. It's definitely explainable. And Snell's law has got, I would say, 90% to do with it, because we are looking through an atmospheric, it's a medium. We are looking through something, and this something is the air. There's water, there's oxygen, whatever's in our air. Um, uh, yeah, light travels through that, sound travels through it. And there's a difference between them. So what I did is I wrote the paper on my findings. I've put the math in there. I've given the predictions, and the two predictions in the paper are what I originally did. The original pictures, the drawings on the front pages, this is where I came up with the whole idea to try and measure it on a smaller scale, is when I saw the miraging occur on a vertical wall. And that's when I first did my test, was on the vertical wall, and I said, wow, I have to test this on a larger scale. I did it on a larger scale on a road and on a lake. So I've used a vertical wall, I've used a tar road, and I've used it's a small lake. It is a 250, I think it's 150 meter lake, but we did a 250 meter distance. So I went further with the camera, but it worked over the lake, worked over the tar road, and it worked on the wall. Each time math worked. The predictability with the math that I have come up with has worked to be able to predict where we would see an inferior mirage. Yeah, guys, any questions? I did ramble quite a lot on there.
Thank you for that explanation. Is there any part of this paper we should maybe dial in on specifically, Dan, that maybe you had some questions about, or Jesse, if you've had a chance to think of anything you might have issues with or suggestions for?
I'm excited because we've had so much confusion at the surface. I was desperate for two terms that came up in his daily vernacular, something that I kept calling a convection line, where surface heat was rising and constantly being replaced by cold. So there was a turbulent surface that he describes as a boundary layer. And it seems apparent, a lot more in infrared. And that's where I noticed it anyway. And I was looking to name that. And also I had a huge problem describing what I called horizontal refraction, which I kept talking about rolling up the window of the car and putting another window and another window. And eventually you wouldn't see so clearly mile after mile. And we'd have not refraction as described, because they've claimed over and over again two things of a gradient, being pressure and temperature, both very, very atmospheric. And we've been trying to say, yeah, I doubt that's what's going on, because that's up above. Now, Beerman's taken advantage of temperature readings, so he knows more about equating the difference between what I used to call the angle of attack. Nobody knew what I meant. He calls the critical angle. It's almost like critical angle plus temperature. What is that formula you have, that short one?
It's the height versus the critical. Oh, it's the different mediums. You'll get the. Oh wait, let me take a step back.
Height
you got the distance equals the height
times angle. Height times angle equals plus temperature.
So you get the distance. To work out the distance, you need your height, and then the two different index of refractions. So with that data, you'd know at your height. So say you 1 meter, your observer height is say 1 meter from the ground. You have the two index of refractions. With that index of refraction, with that information, you can calculate the distance that you would see the total internal reflection occur. Otherwise, you're going to be seeing refraction occur, and that's when you're seeing displacement of target. So it's, for instance, a road mirage. We're seeing the road mirage typically occur about 200 meters away from us on average. It's such a minuscule amount of difference between the index of refraction, even if the road temperature is 50 degrees Celsius and the air temperature is 20 degrees Celsius, or if the road temperature is 40 degrees Celsius and the air temperature is 30 degrees Celsius, it is uh, there's not a big difference those two different mediums. It requires distance for you to see that reflection occur, which is all in the math calculator or calculable. Is that the correct word? But it's all in my data as well. So I've used different data. I went on different days, had totally different data, and I could see that, for instance, on a road, we see it typically at about 300 meters, where we would see mirage occur, and that is angle. So that angle is, and if you take a straight line towards that tarmac, that is I think you call it the angle of attack. That is calculated as the critical angle where you would see total internal reflection occur, or you would see refraction occur.
The great news amongst that conversation is what he's saying is it's predictable. He just wishes we're running out there and showing how demonstratable it is, because he's had the limit of working alone, or with his, family, and at, smaller distances.
I would love to do this over a longer distance.
So we're electing Jesse to do the work. Fortunately,
that's actually why I reached out to Jesse. Yeah, go ahead. Sorry, Dan. I'm just saying that's why I reached out to Jesse, because he got really cool to do this even more.
Mm-hmm. Jesse, can you describe some of the varied things you've seen when you were working, and where you were at versus what this conversation might do for you?
I'm not sure how to answer that all exactly, but I've seen a lot of the same things that Beerman's seen.
Did you have any concept of it? I mean, you and I were lost, right?
Well, I mean, I understood it just as ray bending in density gradients. I had never thought of trying to quantify it with and see if it fits Snell's law. So I think that's very interesting.
Yeah, so what you do is, to get the critical angle, you got to get the arcsin. This is, the university is helping me to figure out the wording and the math, and they gave me the calculations to work out the critical angle, and that would be the two different refractive indexes. If I'm not mistaken, it's the math is in my paper as well, but it's the one refractive index divided by the other, which gives you the critical angle. With knowing that critical angle, you would say the distance equals the height divided by the tangent of the critical angle. I may be botching the verbal explanation. The math is available on my paper. It's all in my calculator, the application that I developed. I am a software developer as well, so I put the math into an application. So I developed a little basic application where you can put in your index refraction into this calculator, and you can click calculate the distance, which will give you the predicted inferior, where you would see that inferior mirage occur. So yeah, it's all in the paper, so you can do it manually, but I do have an app developed for it as well.
So how do these images you're searching for right now, Dan, correlate with Beerman's findings?
The inversion, we understand as soon as something's upside down, mirrored, we understand mirroring, but mirroring off of what is what he's saying. He's saying eventually you essentially hit a brick wall of air, and that's surprising. I wanted to ask him again to help me describe the horizontal banding we're seeing, and at what point. I mean, I've got some very good examples of what appears to be water um, bulging that I'm being challenged by, and then yet I have examples of areas with no bulging whatsoever. So I think this will clean up the optics part of it, but I'm not sure how I can get people to come closer to measure the, for flat Earth I need to measure the geometric horizon. All of this stuff is proving to me what people are seeing when they're seeing bottom up obstruction. It's not due to the curvature of the Earth, although you've determined, in your findings that it's probably still a globe. I think this helps me a great deal to bring people closer to actually measure the curvature of the Earth and stop measuring this and calling it atmospheric refraction, because it's not. It's all off the surface. This is all about surface behavior, not about the atmosphere. If I'm mistaken, please correct me.
Yeah, so what we are seeing when we're looking over a distance, specifically over, let's use water for an example now. So let's say, yeah, in Cape Town, we've got ocean temperatures of 16, sometimes 80 degrees Celsius, and the air temperature being about 25 degrees Celsius. When you look at those two refractive indexes, they are very, very similar. So it takes a very, very long distance. I think it's about 3 kilometers before you would see total internal reflection occur, because those two mediums are so similar. But there is still a difference between the temperature at sea level and just above sea level. But it's so minuscule that for us to see that boundary layer or see that total internal reflection occur over that boundary layer is quite a long distance. I would love to measure it, but like I say, objectively, but like I said, if anything, when I look at a distance, know where Island is, for instance, that's 7 kilometers away. A lot of the times I see total internal reflection or a inferior mirage occur before then at 1 meter above sea level, and I say, oh my god, this is so, it's going according to the math, according to prediction. I would love to go firm measurement, but I can only imagine that it's still going to be accurate, because I do believe that is what's happening. Like I say, it's been 95% accurate up to 300 meters. That's the equipment that I've had tested with, and it's up to 300 meters, where I say up to, meaning try it from 5 meters all the way up to 300 meters or 250 meters. I can get you guys the Excel sheet if you do require.
So I got on my screen a couple of examples of the same span, one with a lot of mirror and one without. So can we deduce that that's just a temperature phenomenon? In other words, if the temperature increases, all of my TIR, total internal behavior reflection, that'll start to happen just because of temperature. In other words, same day, same weather, same location, same height. As the heat arises and starts to bounce off the surface, is that exclusively when this will happen? Like temperature, it's temperature driven, correct?
I wouldn't say it's temperature driven. To be precise, I wouldn't say it's temperature driven, no. It's refractive index driven. However, in saying that, temperature is involved. So there's a standard refractive index per temperature in the atmosphere, but it's not 100% accurate. There are tools to measure it precisely. It's called a refractometer or refractometer or something like that. It's quite expensive here in South Africa. In the US, it's dirt cheap. I'm hoping one of you guys may buy this one day if you do take this research seriously. But it's dirt cheap for you guys. Actually take the exact index of refraction. I believe you will get 100% accurate predictions of where you would see an inferior mirage occur. When we're seeing on your image the furthest one, the one says mirror of bit of mirror of fact that the tangent is lobbing. Oh, sorry, it's very blurry on my side. That one you got over that you had open in front now, where we see that mirror lining. Yeah, that one, where we see that mirror line, that where the two images are cut in half. If anything, I believe that is where the actual horizon is, but it's behind that. It's weird, the boundary now, but that is what's cutting that target off. Is that hard cutoff line, and that is where it is. But it's behind. It's hidden by mirage at the moment, and you see that on my wall footage that I've shared as well. And I've done that on different days.
Now, when you say horizon line, of course, it's optical and apparent. Can you help me?
No,
No.
in the physical horizon, I believe that's the physical
The
horizon.
physical horizon is 5 miles prior to this. Yeah, you understand. This is a 10-mile span, and from this height, the horizon's only 3 miles away. That's the whole.
I don't know the yeah. So I'm not too familiar with the scenario. So what I'm saying is, with my footage that I've shared with the wall, for instance, when I go low down on the wall, and the wall I know is I've showed footage. There's an entrance that goes into this building, and whenever there's the inferior mirage is cutting the target off, it's always at that end of that wall, where that's the physical wall, but you don't observably see the physical wall. You see the cutoff line. But when I change the angle of the camera, where we don't see total internal reflection, you see the physical wall, and that's where you expect the cutoff line to be. I can share that video as well if you want to see it. That's a very, very small scale. I've shared it on a curved road as well, where you would expect to see the physical tarred road curve to hide the target. It's the same optic visual thing that you see, the same observation that you see over a long distance in real life reality, versus a small scale experiment. And once again, it's predictable where you would see the inferior mirage occur, and that is what you would always see before you see the actual cutoff line, because the physical actual obstruction is covered by a inferior mirage, even if it is 0.01 millimeters thick, because of that critical angle, which is, once again, like I say, testable and measurable.
So my suggestion, and I need your input now, is if I come out here early in the morning, which is in the case of the mirrored image you see on the left, they didn't get the balloons filled very quickly. They had to go get extra helium, something, but it was well into the heat of the day. In other words, at the beginning of the day, I suggest that you could blatantly and easily see across this span, and see shore to shore without anything close to obstruction, shore to shore. I have images of cameras without the mirroring. So obviously the suggestion is going to be, for instance, here, here's what it looks like looking across. When the heat comes in, you're fucked, to be honest. So what I'm asking you is, would it surprise you if we did not see this effect in the coolness of a morning, or the more balanced temperature of an evening, where you don't have sunlight directly on your subject?
So I don't believe the sunlight is going to
Well, it's causing
make
the
me
heat.
say,
It's causing the heat. The sun's
yeah.
causing.
But if that water is warm and the outside air is cold, there's going to be a temperature difference. Even if it's 3 centimeters thick, there's going to be a temperature difference. So the inferior mirage may not be large. So yeah, you would still always see an inferior mirage occur, even if it is only 1 millimeter long. So you aren't able to observe it, the full inferior mirage, but there will always be one there. I don't think we're able to see the actual physical horizon. As ironic as that may sound, I know it's fucking disheartening to hear. But what I mean is, 3 centimeters below that would be the physical object, the actual water. In my case was the wall. Even though it was only 1 centimeter below the mirage, it is there. It's I know it's there. I can touch it.
Okay. I've watched this change due to temperature, so I guess what you described is what I would call minimum refraction. Where they use average a great deal, but where you're saying we may not even notice it, they're calling it minimum refraction. They're still using the term refraction. Can you clarify for me the difference between atmospheric refraction and total internal reflection? Because
Yeah,
they're both present,
so
right? They're both present.
correct, 100% correct. So when I talk about total internal reflection, that's when we don't see through that medium. So we would see the inferior mirage. That's the actual object that we are seeing. When we see refraction, we are seeing through that medium, but we're seeing it displaced because it's still the same light coming towards the observer, but it's coming at a different angle because it's exiting one entering the medium that the observer's in. When we're seeing total inner reflection, seeing the image, which is now the inferior mirage, in the medium that you are in. You're seeing it reflect on that boundary layer where you would typically see refraction. If you don't understand that, I can try explain it a little bit better. I do have a drawing that can possibly help my name, but just to reiterate again or explain again, is when we're seeing total internal reflection, we're seeing the same light within the same medium that the observer's in. When we're seeing refraction, we are seeing light come from a different medium entering the medium that the observer's in, and because you're able to see the light, that's why it's displaced, because it's coming from a different medium, but it hadn't reflected off that boundary layer. It's refract into that through that boundary layer. It's actually exited the boundary layer, where internal reflection does not exit the boundary layer. It remains within the boundary layer, and that's why you see an inverted image.
What do you say to examples like I'm throwing up now where we don't see it, where we're able to see things very low into the sand, um, like very low? In other words, we're down there at that surface, but we're not seeing any optical obstruction uh, off the surface
Yeah,
sometimes.
there would be no total internal reflection in this case.
So why?
There will be minuscule total. Minuscule. Yeah, Jesse, you go ahead. You go ahead. I've spoken a lot. Go ahead.
Well, anyway,
I will touch on it though as well.
let's see. Could I share my screen?
Yep.
So Dan's gonna have to stop sharing if you want to share. So you guys gotta pass off the screen share.
Let me get rid of mine. Boom. Think I did.
Yep. Okay. Can you all see mine?
Not yet, no.
I got it.
Is it not showing yet?
Well, you added colors. How attractive.
There we go. I got it.
Oh, good. Okay, so this is just very simple here. This is just a fish tank picture, but I flipped it upside down so we could think of it as, having the hot less dense down below and the more dense up top, like hot pavement. so that we can talk about the total internal reflection. So what I've drawn here is this red. Is the red overlay show up okay?
Yeah, can you
Yes.
set it up again though? Where you inverted what? So it looks like what? And where's
The-
the ground? And I'm confused.
It's an upside down fish tank, Dan.
That part I got, but I don't know what you're trying to demonstrate by inverting it, or why you said some, concrete or cement and density. Where's the ground in this?
The ground would be down
And okay,
because
where,
okay, let me draw the ground.
or the surface? We shouldn't say ground, right?
Okay, well, I'm going to draw a hot pavement. Most of Beerman's experiments have been, at least in the pictures, were over hot pavement, right?
Mm-hmm.
Correct, because they are easier to get closer. When you're looking over an ocean, the gradients are so similar. It's a massively different distance, a longer distance, so it's difficult to get the measurements in.
Okay, so we're going to represent the surface here. And we're going to get some temperature behavior. And what's the red line again?
That's what I would call the boundary layer. That's where you see where that light is reflecting off that red line. Below that is a different index of refraction than above that red line. But where that red line is, it's actually quite a cool illustration. There would be slight bending where mainstream says it bends in a longer arc. I don't believe that is occurring because I've measured the temperatures quite close to each other, and there's quite a distinctive difference quite close to each other. It's not a gradual. Yes, it is gradual. But it's not as gradual as what I've been reading. And Andrew Thomas Young doesn't even bloody talk back. But reading through his papers, it doesn't match the. So yeah, there's a big difference between the two, and that's where I get the boundary layer, and that's where I'm saying that is it's predictable, it's measurable, which is really really awesome.
I agree. Thank you for your effort.
Okay, is that better, Dan?
Well, I feel we could cut off the bottom now because we don't need subterranean stuff, but okay. I'm looking at I would say heating a warmer day
So
starting to happen here.
so the red band represents the gradient between the hot air right close to the hot pavement and the cooler air from above.
It's not a gradient though. It's a boundary layer that's producing temperature. It's not it's mixing. It's I don't it's not part of the atmosphere, I'm sorry, is what I mean.
Well, it's made of air and it's a gradient. It does not have a zero thickness boundary layer between um, hot, a homogeneously hot layer and a homogeneously cool layer. It's a gradient. That's the definition of a gradient is a gradual change between two different, say, temperatures in this case. If if you had like a cellophane strung out or something to completely stop the mixing of the hot air with the cold air, then you could get much closer to a boundary between the two densities of the mediums. But because there isn't, and there's turbulence, and you can always see the turbulence, there's always a little bit of ripple. Um, there's definitely a gradient there. So anyway, what I'm illustrating here is here's the laser on the left. and it's coming down, and it's going essentially straight while it's in the homogeneous cooler upper air. But then when it gets into this gradient near the hot pavement, it begins curving up. Now, if the angle is too steep, or the gradient isn't strong enough or thick enough, then what happens, can you see this line that escapes and shoots down and hits the pavement? So instead of curving up, it'll actually escape, and then it won't be total internal reflection. It'll still be deviated from its path some, but it breaks out and hits the ground. But if this gradient is strong enough, if it's got enough degrees per vertical meter to redirect, to curve this back up above horizontal before it breaks out of the gradient layer or hits the ground, then it's on an upward path and it doesn't escape, and that's total internal reflection. Now, I think that Snell's law might not model this exactly, because Snell's law assumes a zero thickness boundary layer, but who knows, maybe it does, because you can see if we instead we had a thinner, much more dense boundary layer, and the same amount of curve happened within a much smaller region, then we would have, where did I label that? This. You could see that the light would have to come in a different location in order to come out at the same location. So that's the only thing I see. And I also don't know exactly how closely I don't know what effect the thickness of the gradient has on the exact angles involved, but I still think it's very fascinating.
So yeah, Jesse, perfectly well said. So I agree. Snell's law would not be it would be from like a piece of glass, for instance, or a super thin piece of paper glass, and then it would bounce off it. That's not what I'm saying. What I'm saying is the gradient that you showed there, for instance, between the on red line that you had going across. I agree. It's bouncing, it's curving through that because Snell's law is taking place at boundary layer versus boundary layer. There's hundreds of boundary layers occurring there, which is bending, or not bending, but it's changing the direction of the light each time it's hitting a boundary layer. But the cool air, you have cool air, and then just above hot pavement, those temperatures are reasonably stable within a certain amount of height. So, for instance, I remember my wife and I, the highest we got, where we got very stable above the road, was 3 centimeters, where it remained 42 degrees, 42 degrees, 42 degrees. Then all of a sudden it went 39, 36 in a small amount of space, and then all of a sudden it went to 25, and it just remained 25. But I'm talking about a maybe 30 centimeters to maybe 50 centimeters, where it was this gradual change in temperature, but there was a distinctive difference between the cool air, like on your image, and then it just above the hot pavement. It was stable in those areas, and then there was this patch where it was gradient, where there was a gradient, and that's I believe that's where the curve occurs. And like I say, you're able to measure that distance because you've got the cool air above. That's why I always say measure it about 30 centimeters to a meter above the target, or above the surface that you're measuring, and then about up to 3 centimeters, maximum 5 centimeters, to get that to get where the boundary layer would be between the two. But each day that we went, there was a distinctive difference between the cooler air and then the air above the surface, and that's why I say total internal reflection occurs near the surface. But the same thing occurs when we see a superior mirage. That's a very rare condition, though, or the Fatima uh, to correct myself there. I'm talking about the Fathom Garden. It's very rare, but you do see it. It's basically you're seeing the same thing, but you're seeing the next boundary layer above the observer. And it's the same thing. It's measurable. It's testable. If you can get 2-3 meters above the observer and you can measure where that difference is, you'll be able to say, yeah, you will see a Fathom Garden on this day. It's definitely testable. It's measurable. 100%.
Exactly. And that would be caused by a stable density gradient where you had a very dense layer that you're in, a very dense core, a section where you're in, and then at some point above you, it changed to a very light, a very low density region with a relatively narrow gradient zone. And then any light that was going upward from the object you're looking at would hit that gradient zone and totally internally reflect back down towards you, giving you a upside down image of whatever you're looking at, but above you, just like there was a big mirror up there.
Correct.
Yeah.
Yep. And before you get that internal
Go again,
reflection,
you cut
before
out.
you hit that critical angle, you're going to see refraction. Oh, sorry. Before you see the total internal reflection occur, so where you don't see the above inverted image, you're going to see refraction, and that's when you're seeing an object that's below where it's supposed to be being presented a higher above, because that's where it's leaving that boundary layer. But because it hasn't total internal reflected, instead it's been refracted, and that's why it appears higher than what it actually is. Very, very interesting. That's what I came up with in the research, and that's when I realized, oh my God, this makes a lot more sense. Yes, it does deviate a bit from mainstream, but I've done my own work at least, and for me it makes sense because I'm able to measure it, and that's why I shared this paper.
Did you say something appears lower than it is with a bottom
No,
heavy
no,
density?
it appears higher.
Oh, okay.
It appears higher than what it actually is.
Yes,
Sorry,
yes.
I may have misspoken. Yeah, it appears higher because it's lower, but it's that light is, instead of being totally internal reflected and that we don't actually see it, we actually seeing it come back in, being refracted into our medium that we are in, and that's why we're seeing it. So it's
Right.
like your image here, just reversed.
Right. Exactly.
Yeah, it's fascinating. I was absolutely amazed by seeing this and actually measuring it, because you remember my previous research. I was under the impression that we see vertical lenses in front of us, and I couldn't get it quantified. And when I took a step back and I really put the math to it, to try and quantify something, then it made a lot more sense to me, which is awesome. That's when I was able to predict we would see an inferior mirage, and like I say, as well as a superior mirage, which is a lot more difficult, at least with basic equipment. And that's when I contacted you, and which is awesome because I think we can do it together.
I did have some ideas for ways of quantified testing of your theory, and that is in a fish tank, because with a density gradient, because we can measure the mass density of the water column at any depth by hanging, like, say, if we take say a 10-gram fishing weight, hang it on a thread on a milligram scale or whatever, and we can lower that down into the water, and we can measure the displaced mass of the water at any depth we want. So we can actually measure the mass of the water at different depths. And then obviously we can take a photo from the side view of a laser beam going through it, and we can then measure the angles. Do you see what I'm saying?
Yeah, but my math requires the refractive index. So that refractive index, there's a quantified amount which will give you the calculated critical angle, which will tell you the distance that you need to be to reach that critical angle. So, for instance, if you take a triangle, the angles it's always going to be the same, but you're not always going to reach that critical angle. For instance, if I'm 1 meter above me, 1 meter above the ground, and I'm looking 5 meters in front of me, that angle is way more steep than if I'm 300 meters back. It's going to be a much more open angle. Do you understand what I'm saying? The further you're away, the angle needs to open up to remain at that height.
Yeah.
Yeah,
Well,
yeah.
it's just
So
an idea.
yeah,
Because we
yeah,
could
yeah.
measure
So
we could measure the refractive index of the fish tank medium at different elevations.
100%. So yeah, that'll be awesome if you do it in a fish tank, because yeah, then you got even control over it as well, and it's definitely testable. And like I say, you guys in the US, just you can search it. You get a refractometer or refractometer or something. You get them for wine, if I'm not mistaken. Um, but for me to get it here in South Africa is going to cost me quadruple the amount what you guys are going to pay. I think it's about $50 maximum. For if that.
Oh,
But
those are
for
for
me
liquids.
to
Yeah, those aren't for
yeah, yeah,
air, they're for liquids.
yeah. So the one for air is about the same price, but if you want to use the one for the fish tank, you would need to use the liquid one. But it'll still give you a refractive index, which you can put into the calculator. So you just need to get the two different ones, so you can get a number that you can get a critical angle. But yeah, the air ones are about the same price. But yeah, we don't have it locally here in South Africa, so I would have to import it. The universities may be funding this. I'm still waiting for a response. I've spoken to them. They very, very interested because it's quite fascinating because there's nothing else on this that I could find that they could even discuss with me. They helped me with the math, and yeah, I am where I'm at now, which is really, really awesome. And it's been predictable, which is what's really sparked a fascination on their side. But to get the funding is not as because it's not. I believe it's changing. It's definitely something new. Um, I'm just hoping to get more support from it.
Here
I
I've
agree.
drawn kind of what I think the upside down mirage would look like. What you're talking about, the light rays go up and then they hit the gradient and then they curve back down, but because they're crossing over, the reflection looks upside down. See how they're crossing over each other?
Almost, but that would be that it's very difficult to draw. I have a drawing for it to show how it would the boundary layer to be a superior mirage. This would still be a drawing for a superior for a Fata Morgana where we see an inverted image. I do have a video that I shared. I'll actually, you guys, you and Dan chat. I'm gonna find the drawing where I show how it would work, how you'd see the superior mirage.
Oh, does superior mean right side up? I never could
So,
remember which mirage was which type. I just know if it's a lifting or a sinking, and whether it's right side up or upside down. That's the four combinations. That's all there is. Plus combinations of those to make
yes,
it.
yeah. So the Fata Morgana is like an inferior mirage, but you also see the superior mirage with it. So you see an upside down, the same target upside down above it, but then above that you see the right side up of it. That would be the absolute superior of it. But the inverted image of it is because it is being totally internally reflected above the observer because there's another boundary layer above the observer. But because it's not exiting, because of the, I believe this is because of the shape of the Earth, and that's why we're seeing it because that's the only thing logical sense, at least with the prediction. That we're seeing a curved boundary layer, and that light is it's not bouncing off it or off the boundary layer, it's actually refracting back into the medium that the observer is in. But you would have to have a curved surface, and that's why you would see a superior march. Um, for me, at least, I'm not saying it's because I'm a low birther. I'm just saying this is for me that said, wow, it possibly is not flat. Because I was intrigued by flat Earth, but I do not believe it is anymore. At least with my research.
Well, what do you think of this? See, these rays down here, they're they're just being curved, but they don't cross over. So that would be the image of something being lifted up, but not turned upside down. These upper rays, they go up and they do total internal reflection, and then that inverts that image. So this is kind of like how you would see a ship lifted up and right side up, and then lifted up even more and upside down.
Yeah, then you would be in the same medium, so you would have to have the same temperature. So yeah, once again, that would displace the target. But I think when I'm talking about the superior mirage, I'm talking about those floating ships, ones that you would not expect it to be where it is. But yeah, the one you're showing now is similar to when you look at a distant object above a fire. It's the fire's airs is creating a bound layer and it's displacing the image. Same thing what you're showing there.
Oh, are you talking about the ones where the ship is only appears once, only appears right side up, and shows no indication of any distortion, and yet it looks like it's way up in the sky?
Correct. Specifically the ones that are very far out at sea that you wouldn't expect to be able to see in a large size as well. Those would be superior mirages.
Do you have an example of that? Let me stop my screen share because I want to see an example of that just so I know what we're talking about.
Yeah, let me find one for you. Maybe you and Dan chat a bit, and then I'll see what I can find here for you.
Hi, Jess.
How's it going, Dan? Why are you so quiet?
First of all, this life of arguing is exhausting.
Oh,
And I kind of have a crunchy ending that I don't want to introduce unless you want to hear it now. I mean, if I share my screen, I'm going nuts. But I mean, I should let you guys finish. But I am going nuts.
Yeah, let's save the fun for the end. But maybe we can, if anyone has any questions, we'll have a time for that, or even maybe now be a good time to pop a couple questions on while Beerman finds his.
Yeah, let's save the nuts for when.
But unless you had something.
Yeah, no, I do. I can
Right?
put it in English. That when the flat earthers are accused of cherry picking the perfect conditions to be able to see line of sight, and I disagree entirely. I just think that that's normal conditions, and that the factors on vision that he's describing are beautiful to me because I'm looking to measure stuff at 1.2 miles away. None of this distant stuff. I've been trying to say the whole time, this distant stuff is not the curvature of the earth. It's distant stuff, but I could never explain it when they go, well, what is it then? You know, bottom up obstruction. What is it then? Beerman's telling them this is what it is. It's not always there. And that evidently the two factors would be angle and temperature.
I'm unable to share my screen.
That's odd. No one else is sharing theirs.
It says you can't stream this channel.
You might be in the wrong.
Hold on, let me see if I can. Let me see if I can. If it's a.
Maybe he needs some
Might be a permission thing. Yeah. My phone is really not, and I'm streaming on my end. If somebody could like click them and give them the right permissions.
Oh,
Otherwise,
my phone is super like it's lagging so bad right now. He doesn't have.
There's a role called share screen / camera.
Yep, that's what he needs. There you go.
And he's got it now.
Yeah. Do you guys see that?
Oh yeah.
Okay, so for instance, this ship below my mouse now, you can see my mouse, right?
Yes.
Okay, the superior mirage is above my mouse. So this target, this is what I'm talking about. Yeah, this is when it's exiting the medium.
Oh right.
This is basically a. Yeah. So this is where it's exiting the medium that this is going down towards the horizon. This is as much as it looks like it's vertical. This is not vertical. This is horizontal above us, going further and further and further and further away. We are seeing this is the Fata Morgana. This is a total internal reflection occurring above the medium that you are in, and this is where the light is not total internal reflecting, but it's actually refracting. So it's coming from further back down here, but it's instead of it going above the observer, it's actually refracting and coming towards the observer, and that's
Right,
why you're
so
able to see it. And
so
this,
what we're
yeah,
seeing on the
go ahead.
top starts out above the strong gradient zone, right?
So this gradient zone is coming above us all the way along us. So this is it. This is above the observer. This is beyond wherever the horizon is behind this. This is not a vertical thing in front of you like 90 degrees. This is actually coming towards the observer. So let's say I put my mouse here. It's coming towards the observer and it's over the observer now. So this is the total internal reflection above the observer over here, and it's actually exiting the medium on top over here. So if you had to turn this upside down, I actually got a video on my channel. Let me get that up.
So well, you're
I got
saying
it on
there's
my
no more
sunset video.
there's no more surface noise at that point. Is when you say it's exiting the medium. I think you need to put that in layman terms. It's exiting the point of heat turbulence, or
No. So
or
that's
is
the
it the
boundary
angle,
layer.
or is it exiting the angle? Are you change? Is it your angle change what's making the difference? Because now you've got an angle change as well.
So yeah, because it's not reflecting internally. Like wait, that's not a good example. Hold on, I did a video about. I have done a video about it. Give me a sec. It could be this one. I did share it with a lot of the. Oh, here we go. This is the one I'm looking for. So let me pause
Would
this.
you mind making
So
that
this is,
full
for
screen
instance,
if you could?
Is that good?
Better, yeah. Thanks.
Okay. Hopefully this is the video. Well, this is what I'm looking for, but I got more in it. I haven't watched this video in quite a while either. But we're looking at a road mirage here. What I'm doing is I'm flipping it in this section the other way around. So we are seeing total internal reflection occur over here, the same as we see it in the road mirage over here. We are seeing, for instance, this would be a Fata Morgana, but we would see this little car would appear over here as well. But because there's a road now, we're not able to see it. But what I'm saying is in this section, because this is a medium running through here, but we're only seeing total internal reflection occur at this angle. But there's still there's still that air temperature coming towards the observer. There's still air over here. But because we're not at the correct angle, we're not seeing reflection occur over here. We have to be at the correct critical angle to see total internal reflection. Does that make sense? Do you understand that? Do you have any questions? I'm really botching this, I think, but yeah, let me know if I must restart this, and I'll start from the beginning. I really jumped the gun there.
I think we need to go back to the ship for you to describe it again.
Okay.
This is really hard to
Okay,
visualize.
no. So let's stick. I'm gonna just take it a bit slower. I'm a South African that rambles a lot.
If you could just work on the
Okay.
top one, the two bottom ones are confusing.
Yeah.
All right.
Cool. Let's work on the top one. We are looking out towards this road. Why are we seeing this occur over here? Why are we seeing the car being reflected over here? The reason for that is there's a different air index of refraction occur just above the road surface, and that's this layer here. It's about 2 or 3 centimeters thick. Does that make sense? Do you understand that?
First of all, is the lighter color sky reflection the lighter color? That's sky.
All of this is all reflection. This is the
reflection
mirage.
of the sky. Was it the distance? Or
This is the sky. This is the sky. It's everything. This is whatever's above it. It's being reflected on this.
Upward, you think it's upward or forward? What's being reflected is forward. Probably not upward, right? It's distant sky or something.
It's at the angle that you are looking at. If I had to throw a ping pong ball, say that's a piece of glass, I throw a ping pong ball at this angle, it's going to exit at that same angle, the opposite direction. That's what we're seeing.
So it could be mountains or sky, whatever's off there in the distance that we don't
see.
Okay.
But you see this distinctive line here in the road.
Yeah, and also the length of your reflection shows you the angle. It's longer than the truck, right? So it shows you a
Yeah,
really
no, so
strange angle.
yeah, don't even worry about that. I'm just this. You see this distinctive line, correct? You see that.
Mm-hmm.
Okay, so that distance is measurable. That's where my calculation comes involved. Where I'm saying I can measure it up until there. I'm able to predict this distance, and everything beyond that distance is going to be totally internally reflected on this medium, on this boundary layer. So what I'm saying, because there's a layer that it doesn't start here. This layer is all the way till the observer. It's beyond the observer, behind me, for instance. This is not my photo, but if I am the one that took the photo, this medium is there. It's undisputable. It is there. You can go measure it. I'm sure you can even take a glass of it. Do you understand that? Or do you think it's only happening here? Because if I drive further along the road, this moves along with me. This is always going to be here. There's this boundary layer that's occurring here.
Optical illusion, so it's not happening anywhere.
No, it's not an optical illusion. No, it's think. Let's say this is a rainy. This is a rained road. At a distance, or if I'm right there on the road, I can actually see the tar because my angle, it's not reflecting off that water. I can actually see the tar. But the further I am away from where I'm looking at, I'm not going to see the tar anymore. I'm going to see a reflection. Those are two boundary layers between the water and the air. What I'm trying to say here is between this tarred road here, there's still that air. The same air that's over here is over here, but because we're not at the correct critical angle to see reflection, we are seeing refraction. So this is all actually refracted. It's so minimal, but it is refracted. It is refracted. There's a boundary layer here, which is why the math works, is why you can see total internal reflection occur. So what I'm trying to say is the same thing's occurring in the reverse. So I'm reversing this to show you, yeah, we are seeing total internal reflection occur with a Fata Morgana, and we're seeing refraction occur, yeah, because it's not reflecting off this layer anymore. We're not reflecting over here. We are refracting because we're not at the correct critical angle. It's too close for us to reflect. The angle needs to be much closer, more open. At like 1 degree, 1.0 something degrees. But because we're not at that angle, you've got to be further away to get that angle. We are seeing refraction, but it's very minuscule refraction, but there's refraction occurring here because it's exiting the medium. It's not remaining within the medium. So it's no longer, over here is not total internal reflection. Here is total internal reflection. Here is refraction. Here is reflection. Same thing. Refraction, reflection on this boundary layer.
Mm-hmm. So
might have more, yeah.
If I was to say accidentally at some point to someone that there was no refraction,
yeah,
and then be corrected, like let's say Ruhif would correct me that there's always refraction. You're saying that in the pavement area at the bottom of this picture, there's just lighter version of refraction. So I just want to display to people when they tell me there's always refraction, that doesn't mean it's having an effect on what we're seeing.
Very minimal, correct.
Thanks.
Depending on the conditions, though.
Mm-hmm.
Which is, like I say, measurable. And you can use the math that I provide in my paper, because, like I say, I've tested it. I do have my paper, the data here. Can you say?
And what are you going to call that point? It's not a horizon. What are you calling this front where your arrow is now? What are we calling that? Your predictable distance? What are you calling it?
It's the distance to the mirage. So this is the data that I did. So wait, let me get this open again. Hold on. Are you saying, what am I calling this?
Yeah.
So this is the distance to the inferior mirror. This is where we see total internal reflection.
As far as I'm concerned, this is bottom-up obstruction.
Yes, so we would always see bottom-up obstruction covered by mirage, but there's more to it. For instance, on the wall mirage video of mine, the wall is actually the main obstruction. So I can get that open. Give me a sec.
The road is completely obstructed, by the effect. Not.
Yeah, but it's so minimal. So this wall, for instance, of mine, this is not my wall.
Explain to
Let me
people
just
what
get
this
the.
is. This is turned sideways because he
Ooh,
was,
okay. This is not.
vertical is vertical.
Yeah, I got the other one. Hold on.
So when he shows the wall stuff, he's trying to show a surface that isn't necessarily vertical. I mean, horizontal. Switching from
So
horizontal.
yeah. So yeah, this is a vertical one. So yeah, this is actually, you can see the cars in the correct position, but you'll see how minuscule this is, how thin it is. But the actual wall is obstructing the people that walk past. This person is not obstructed by an inferior mirage, but the first bit of obstruction is inferior mirage. It will always be. It will always be obstructed first by inferior mirage, but there's no other explanation why we would see half a building that is obscured. For instance, you would see this as water. I'm doing vertical now, but this will be water. Then we would see an inferior mirage, and we would see half a building. I'm telling you, half a building would not fit in this little section when the rest of the building is the size of this.
Oh,
It does not make sense.
hot wall or cold wall? Which is the
This is a hot wall.
hot
This
wall?
was this is the wall that was 38 degrees, and the outside temperature, if I remember correctly, was 22 degrees.
Wow.
So yeah, there was quite a difference in that gradient. So yeah, you can. So that's that entrance that goes through. I've got various videos of this on my channel. I use this a lot in writing my paper. It was a big help because I could do it on such a close and easy to use location. It was absolutely fascinating. I had my wife walk past here as well. Then I measured that. We stuck bubble gum on the wall to see how thick this was. Even a piece of the bubble gum stuck out. So this was, I think it was about even less than a centimeter thick. This pocket of air that was on this wall that caused that inferior mirage. And then here's the. I'm on push to talk with my mouse as well. So here's all the data that we used, the different days, the different times, the index of refraction, the air temp, the ground temp, the observer height, the distance. This is the predicted distance. So this is what the math predicted, and this was the actual measurement, and then this was the differences. So for instance, on this was 220. Yeah, so the furthest I did was 223 meters. 219 was the actual distance measured. The predicted measure, for instance, on that one was 223.64
You're still
meters.
showing the boat, by the way. If
Oh,
is that what
fuck,
you're still?
my bad. No. I'm showing my Excel sheet. Give me a sec. Did you guys see the YouTube video? Did you see the wall?
Yeah.
Okay, so you're not seeing the Excel. Give me a sec. I'll probably have to stop share and then reshare. Do you see the Excel sheet now?
I do.
Yeah, it's pretty hard to read.
Okay.
I'll call it out.
Yeah, so I'm just saying. So yeah, if you guys want this, I can share it. It's not a problem. It was over 4 different days. First day was various times from 10 in the morning till 3:50 in the afternoon. We did it on various days. In this section here, this was the predicted distance. So the math said to me I should see the inferior mirage occur at 223.64 meters. I measured at 219. As I don't know if I spoke about it in before we went live here, But I did tell you guys I measured with we hired one of those construction measuring wheels. So you put it down on zero and you just roll the wheel. So what I had is, what we did is I said to my wife, okay, she walked out with it and I told her to stop when I saw her enter the mirage, and she gave me the distance of the measuring tool, what it gave us. And yeah, we were out on that first one that we ever did was 4.64 meters. The second time we did it, we were 3 meters out. The next one was 4 meters out. We measured too short, 2 meters. The closest I ever got was half a meter, 0.52 meters, and that was on a shorter distance of 36.52 meters was the predicted measurement. We got 36 meters. It's absolutely fascinating. Like you can see on the data here, we were only a couple of percent out. I would say we're 95 to 98% accuracy with basic equipment. I would love to see what this would do on more accurate equipment or more decent equipment. And this is something you can go do as well. This isn't you don't have to take my word for it. That's why I'm sharing my paper. Guys, please help me do this as well. It'll be amazing to confirm this without me doing it.
I drew a little something up. If you could hop on my screen share.
Yeah, I'm trying to get out of my screen share.
I think you got out because I was able to get into the screen share. Oh, now it
Nice.
says you're trying, it looks like. I'm not sure what it's
Oh
doing.
no, just ignore it. Is it off now?
Yep.
Is that
it's on.
good? Cool.
So this is my analysis of the picture of the barge or whatever that was that said natural gas powered on the side, right side up and upside down.
Got you.
The viewer is kind of probably in the middle of the gradient, and so he can get a view from mostly below the gradient zone, through the gradient zone, and from mostly above the gradient zone. So this bottom set of white rays shows that he's going to see the writing right side up. But the rays are also coming off of those in all different directions. You know, it's not just laser beams, it's every which way, diffuse light. And so some of the rays are going to go up into the gradient zone, do total internal reflection, and then come back down to the observer. But you can see that they cross over right here. And when they cross over, that makes the image upside down. So that's why above the right side up writing, the printing on the side of the ship, he sees a copy of it upside down. But then the top of the ship up here is above that strong gradient zone. So again, he sees the light that's not crossing over, so that doesn't appear upside down. Does that sort of make sense? That's how he sees
100% correct.
What's that?
100% correct.
Okay, cool.
You understand it then?
Yeah, I didn't get the dimensions right. I just threw this together while we were talking, but
Yeah, I understand what you're presenting. Yeah, it's perfect. It's exactly the way I measure it, test it, see it, understand it. And this is without mainstream's involvement. This is me doing my research. I came across this. And the fact that you understand what I'm trying to present as well, dude, well done. Thank you. I'm not too mad.
thanks.
Well,
That
it
makes sense.
Awesome.
Did that make sense,
Dan?
Dan?
it serves me a great deal as well as a flat earth explain these effects, because sometimes, to be honest, if I could share my screen at some point to show you, they're not there. They're not always there, and I think they're temperature driven, and we've seen that many times. And when it comes to curvature of the Earth, you know,
Go for it, Dan. Share your screen.
thanks. This really does show that everything isn't atmospheric refraction, and that the gradient that's always been spoken of is different than all this stuff, and we've been seeing all this stuff yelling it's not refraction, and everyone says you guys don't believe in refraction. So you've really solved a great deal of this puzzle for us. If you look at the top right of the screen, you'll see that during the Nat Geo stuff, this is a very low observer, with the expectation being somewhere between 1.5 feet and I think we claim 2 feet somewhere else. Refraction has not been calculated here, nor has it been claimed. The point is, when you're looking at just a 1.5 foot observer, you look at the bottom left, the obstruction should be here at 1.22 miles, and we don't see any. Also, you'll see the difference between 1.22 and 3 from the same observer height, and we don't see any difference whatsoever. So I don't see curvature of the Earth whatsoever in any of these pictures, but I do experience bottom-up obstruction and incredible surface noise that we haven't been able to explain. And I just can't thank you enough, because it's been awful for us trying to explain to people what causes bottom-up obstruction. Because I believe the curvature of the Earth bottom-up obstruction is a local event, very close and very measurable, but we don't see that. I have
So
not
Dan,
seen that.
So Dan, in this clip that you got open here, specifically the top left, the larger one, you can see a distinctive that band that we I think you would understand the band. I call it the mirage line. But yeah, in the center of this image now, there's a distinctive line. That's when we're starting to see, at least for me, I would say we are starting to see refraction occur. And that's why there's a change in color as well. The light intensity is not the same as it is before that boundary layer. So we're seeing it as clear as it is because we're in the same medium. But when it's exiting the medium, we're losing some of that information, because some of it's being, some of the light being redirected. So some of it's being lost. I think there's a term for it, Rayleigh's criterion or so, that one where it scatters a bit in different directions. But majority of the light, I'd say 99% of the light is coming to the observer, but we are seeing a distinctive difference in the light at that boundary layer. And we're seeing some refraction occur. But yeah, once again, that is so minuscule, but it's occurring and it's measurable. You would be able to measure to that line now, and I would love you to go do it. I think you have the equipment or the ability to do it, and I think you have the drive to possibly do it. So I'm hoping you to go do it. Use the math that I provided, and hopefully it's accurate. I'd love to see the results, and I'm hoping for my sake that I'm correct and it is accurate.
Can I blindly show you something and have you comment on it?
Yeah,
Because
go for it.
I don't know what to think of it now. Because I know that this is a local thing. On my screen is a representation of the distance, and maybe a couple of a power cord in the foreground, a couple of bricks representing maybe what might be the horizon line mathematically. But of course, we have no atmosphere here, and it's just fascinating. And I love this. Everyone says it's stupid. I just wondering what your comment might be if you see this.
So, just could I provide some background information to this?
Please.
The camera is set at an angle so that its lens is as close as possible to the floor, about 1/2 inch above the floor, and you can see the extension cord is almost up to center of, almost up to horizontal. So the eye level is about 1/2 inch above the floor, maybe an inch. So you can see that the actual caster just below the axle stays in the same horizontal plane, because that's how high the lens is.
Okay, wait. So Am I looking at the bottle and the bricks are the is that going to represent the Earth? So I was having a look at the cable and I'm trying to look at the cart the whole time.
The bricks don't even need to be there. Of course, we're looking at the size of the man, tiny in the distance, yet it's only 15, 20 feet away.
That's
So-
apocryphon, by the way.
Yeah. And I just love this because it makes everyone think, what the hell are we seeing in the distance? And it shows perspective more than anything, and how that can take place in a close range. So, can all of your effects that you talked today happen at closer ranges? If it were carefully, I guess, like the fish tank, if it were carefully prepared, we can see effects at closer ranges, right? Like the wall was close.
Yeah, so yeah, we can definitely do it. Skyfree did a brilliant example of a temperature gradient or the inferior mirage that obscured an observation on a ground level in a building. I don't even, I think in their house, 10 or 15 feet. And they opened up the door and it started hiding some of the little objects that they had in the background. Camera's the same height, just off the ground. Remember that the center of the camera lens is about probably 2 inches. If this is a P900, it's about 2 inches off the ground. Those bricks are higher than the actual camera lens. That target that he's moving behind, there's also higher than the camera lens. We obviously get those measurements, but yeah, this is a clear example of perspective and camera height. But this is, yeah, you would expect those bricks to obscure that bottle as it's moving further away, because the camera's center of the lens is, I believe, lower than brick. But yeah, definitely check out Skyfree. She did something. Yeah, she's a she. That's something awesome, something similar to this, but I think even better. Showing the effects that I think you're asking for. And you see those effects happen at close range, 100% you can.
Here's some of that shading and banding that you're talking about across a span, and what should be a single color of gray in the bottom has got all this banding. I really like that example that we see. If you could bring up that with it, where I was talking about the sandal appearing and then pavement and then reflection, then pavement, then reflection again.
Yeah. You sharing the screen, so dude, you're welcome to open up my YouTube and share that video. I think it's the second last video I shared.
Okay. And what do you call it now? That page?
The missing research.
Oh, right. All right, see if I can bust this out fast.
It is the third last video, or the third video on that list of videos.
Anyway, that banding is interesting. Can you describe it again?
Say that again. You broke up.
That banding is interesting. Can you describe it again to everyone before we bring?
Yeah,
Well-
so I believe we got different. Well, we got the gradient, and it's where the light is leaving the medium or reflecting off the medium, and it occurs at different places along the horizontal, depending on the conditions. So if I'm looking over a piece of road, and then there's a piece of grass, and then there's a piece of water, for instance, there's going to be a little bit of a difference in gradient, different height, shape to this. Like, think of it like a big wave. The light's going to exit at certain angles and it's going to enter at certain angles, or reflect and refract at certain angles. So yeah, we're going to see banding along the way. But the more stable the conditions, the less we're going to see of these bandings. Once again, it's all measurable, quantifiable, if you want to call it that. The sandals one is the short distance mirage observations, the third video.
Because I was really
So this road is,
really excited.
yeah, this
when I
road is
saw that.
curved. Yeah, this road is curved and there's a straight section. This is the curved section of the road.
Downhill, right? No, that's another one. Where you
Downhill, yes. Yeah, later in the video you'll see my sandal video. Oh, this is my wife's sandals. Is this the one you're talking about?
You were pointed the other direction. You were left to right in the other one. So that would make it over here.
This is the more straight section of the road.
Maybe we get a little overlay context on this, so get a strike going here. What are we looking at here?
I think that's on a phone call. So yeah, as soon as he's done there. But yeah, this was a piece of road where I could find where we both where I could find miraging, where I could show both the flat section of the road and then the curved section of the road. I think there's two more on my channel where I just did on curved pieces of road, showing trying to small scale demonstrate why we are seeing what we are seeing over a longer distance, why we would see half a ship over the horizon, obscured by minuscule bottom-up obstruction, but it is always obscured by bottom-up obstruction because of the inferior mirage. But it can be a millimeter, it can be 1 meter, but there's no other explanation than physical obstruction. Show, at least for me, I haven't seen it. For us to see half a building or half a ship being obscured with minimal inferior mirage, where we see the actual inverted reflection of the ship. Yeah, if you don't see that, you see basically a hard line. It's like a millimeter on the observation footage for half a building or half a ship. That only tells me that is physical obstruction, at least. And like I said, it's measurable to that obstruction and predictable.
Well, I can't thank you enough for your effort here. I can't wait to show this to the many, many, many flat earthers that have been looking to explain portions, at least, of bottom up obstruction. Because we do see bottom up obstruction that I don't attribute to the curvature of the earth.
I agree. Not all of it is because of curve of the earth. A lot of it is mirage.
Very exciting news for me.
I think go ahead.
I was going to say, if anyone wants to raise their hand and maybe come up and ask a couple questions, I think now would be a good time. But go ahead, Jesse.
I was just going to say, I think the difficulty, Dan, though, is that the one temperature-related phenomena that can cause bottom-up obstruction on a flat surface requires that surface to be hotter than the air above it, and it can only take place in a very small region close to that surface because less dense air does not like to stay under more dense air, and it requires the constant heat to be added from to the air from the surface, and it requires the ground effect to keep it kind of stable because it's inherently unstable. So getting that for a line of sight that is even tens, much less hundreds or thousands of feet above the surface is a big problem for flat Earth.
Could you summarize that again in like quick sentence? What's a problem for us again?
The fact that the one condition that can cause bottom-up obstruction without a curved on a flat surface can physically only take place very close to that flat surface, like within inches, maybe feet, but not hundreds of feet, not thousands of feet, because it's an inherently unstable condition that requires constant input of heat from that surface, and it requires the stabilizing ground effect of that surface. So that's why road mirages are within a couple inches of the road. That's where it happens.
But, but I have examples where there is no dramatic effect and we're able to see what I would call line of sight.
Oh,
So
the other thing I wanted to throw out earlier was when we have these conditions of total internal reflection, there will be reflection. You will see mirroring. That's just part of total internal reflection, is the reflection part of it. If there's no reflection, then you're not having total internal reflection. Go ahead.
right, and my claim is that when it's cool, we're not, and that we're not always having total internal reflection. Sometimes we're able to see clearly in the distance, like clear.
Yeah, so that will be further. So once again, Dan, that will be predictable, but you would most, at least with what I've done, is you always see some sort of obscuring effect. There's something obscures it from the bottom up, and even if you're not seeing the complete reversed image of the target ahead, generally because it's too far away for you to see that complete inferior mirage, and that I believe is because of the shape, because there's a possible curve to it. I could be wrong. I'm just saying that I've been able to measure it, and that's what explains it. And with what you're saying now, when you're saying you're seeing the complete line of sight, definitely go use the math and go measure it, and you'll see it. Yeah, I think you're 100% correct. This is perfect to show this, and this would be because the temperature right at the water surface and just above the water surface are going to be so similar, but there's going to be a difference. So you're going to see slight refraction, but you will always see a total internal reflection occur at a distance. This will maybe be over 3 kilometers if it's extremely similar conditions. But yeah, you do see it. So I hear what you're saying, but go measure it, man. It's the math is there. You can science this shit. It's amazing. It's really cool.
What if I reduce the refractive value of it by having these matching air and water temperatures?
What if you say that again? What if you?
If I have matching water temperatures and reduce all the refractive properties, that reduces your formula down as well.
Yeah, 100%. Then you would see where it actually is. Exactly what you're seeing is what you're seeing.
Well,
100%
Dan,
correct.
if you're going to be there, you're a cool guy. It's going to be too cool no matter what. And I know you're going to be seeing clearly now that heat is gone. But my question,
He's my hype man. Sorry.
Oh, jump the gun on you there, Marty. Go ahead and get your question out.
Boy, he needs like
shit, this summer, when two oceans collide, Beerman, at the tip of Africa, what do you see out there? Is there a bulge always? Is it just mixing and stirring? Is it hot and cold on one side with the Indian Ocean and the cool Atlantic? Is that not a good place to go out peeping?
I've been seeing a lot of Fata Morganas along the coast recently, and we've been having really, really awesome weather. No southeaster, which is very, very surprising. So our ocean water, when I go surf, has been nice and warm. And yeah, when my wife and I go out for drinks or lunch or dinner, oh man, I'm recording the Fata Morganas. It's really, really awesome seeing it, which I never noticed before. So very, very fun.
And then Dan's ocean is fairly, you're always going to have the winds blowing the clouds away there in California, right, Dan? Well, except for if you're in San Diego, right? Have they been sticking around foggy down there, or what's it been like?
Does anyone else have any questions regarding this subject and not the weather? Because I think we should close this so it makes for a tighter video. Less than 2 hours, you know?
Oh, I wanted to respond to something you said, Dan, or asked. If you could measure the water temperature and the air temperature along the path of the line of sight to the nearest hundredth of a degree, and they were within a few hundredths, then that would be very good data. If you only measure to the nearest tenth of a degree, I mean, that a tenth of a degree is all it takes for light to curve equal to Earth. So if the thermometer rounded to the wrong tenth of a degree and it only measured to a tenth of a degree, that would be kind of ambiguous. But if you can measure to the nearest hundredth of a degree along that site, or at least at a few, like maybe, you know, a 1,000 feet out from each end and in the middle, that would really give, that would be some good data.
I hear you.
That would be some really good data. I wouldn't even know what to say about that. If you accurately measured in those 3 spots and you could still see the laser beam when you shouldn't be able to, I wouldn't even know what to say about that.
I also want to respond to Dan's one question regarding if the temperatures are very similar. I just used the math calculator now. Let's say you got a temperature of 25 degrees at the water, or it could be 10 degrees. Let's just say the difference between the two are like 0.1 degree. That's you would see total internal reflection occur around about 3 kilometers away from the observer at a height of 1.4 meters. So if we had to change that to them being very, very similar, we can look at 6 kilometers away before you see total internal reflection. I don't believe that we have had those conditions. Otherwise, you would see something physical in the way. But yeah, get some data, man, and let's run the numbers and do the measurements and have a look at the observation and take it from there. But yeah, that's just to give an example of the distance.
Yeah, that's the exact distances I was showing with the flag before. Exact.
Awesome stuff. There we go. And that's with my math. So hopefully that helps. I'm sure we can take this further then.
How high above the surface did you say that you found the greatest gradient temperature shift?
Myself, it was on the road temperature, it was just above 3 centimeters. Then it had a drastic change to within about 30 centimeters where it was unstable, and then it became stable again. So if on the road, I think it was about 48, 49 degrees. I got, like, it's all on that Excel sheet. And between that temperature and then the stable air temperature, which was for like a meter, 2 meters, the same temperature, or like a point something degree out, there was about 30 centimeters where it changed drastically from the super hot 49 degrees to 38, 36, 34, and then within like 30 centimeters, it then got stable again to 25 degrees air temperature above that. So there was a distinctive line there, but that's that gradient that you're talking about as well, and I believe mainstream talks about it as well. But when I look at what mainstream explains, that they're showing this massively long curved line, I don't think that is what's happening. I think it's going straight. That angle is dead straight towards the target, and then when it hits this gradient, there's this curve, but it's quite a quick curve. So, if anything, if you were a dude 10 kilometers away, it would look as if it's a right angle triangle sort of thing. It wouldn't look like it's curving, it looked like it's actually reflecting. And
Right.
yeah,
The gradient zone for an unstable gradient is very narrow because it's confined to the surface. A stable gradient can be a much longer curve because that's cold air under hot air is a stable condition. So that can sustain it for a lot longer.
correct, yeah. But it'll be very, very minimal change of direction. It'll look like it's on the same damn path, but it won't be like the drawings that they give us, where it's this nice, beautiful curve. I don't believe that's what's happening, or at least the measurements and the observations don't show that.
Alrighty. So, does anyone got any final words about what we discussed here today?
If anything, if anyone hasn't read my paper yet, I think Demons Tried did put it on the website. Go have a read of my paper. The last 2 pages, oh yeah, I think it's the last 2 pages. I've got all the maths there for you guys to go test it yourselves. About 3 pages in, there's the first little bit of math, but all the information is in my paper. Guys, it won't take you that long to read, maybe 15 minutes, half an hour. Yeah, please go have a look at it.
That address is medicinalmass.com in the science section.
Yep, medicinalmass.com/science will go right to a budding source of science information.
I love you guys, man. This really worked out. It's
Yeah,
actual progress. I would say progress.
Absolutely. Thanks a lot for showing up, guys. This was a fun conversation.
Great
Where
stuff.
can we find all your stuff at? Let's start with Jesse on the left and work our way across.
I have stuff.
Yeah, you got a YouTube, don't you?
Oh yeah, I'll drop a link. It's not specifically about Earth shape. It's just whatever I'm working on.
Jesse, can you update us on your current observation that you're trying to make?
Oh, with the 6 kilometer string line.
Yeah, that's exciting.
Yeah, I've got 2 checklist items left to do other than waiting for good weather. One of those is to get the canoe registered and licensed so that I can put a motor on it and use it in the lake legally. And the other is to build a motor mount so that I can use the outboard on the canoe. I think everything else is all ready to go.
Jesse's going to pull a cord line. That's what he's going to do.
The string line. String lines aren't quite as straight as cord lines.
Okay, and that's Jesse Path of Light at YouTube?
It's just from Jesse.
From Jesse at YouTube.
From Jesse. Awesome. And Beerman, where can we find your stuff at?
I got some refraction stuff. You can find it on YouTube. It's called The Missing Research. Yeah, you can find some of my stuff there. I don't post a lot anymore. I haven't been focusing much on this after writing the paper and not really getting much funding for it. But yeah, I think the last video I posted about 3 months ago. But yeah, guys, I got a lot of my work on there. Check it out. And yeah, my paper's the one thing that I'm most proud of. So yeah, I'm open to criticism as well. I'm not here to argue. I'm here to discuss.
Awesome. Thank you very much. How about you, Dan?
Of course, Dan the Waterman at YouTube and Flat Earth Hollywood Live at YouTube. Meetup groups, all that kind of stuff in the Southern California area. Flat Earth representing Southern California area, Flat Earth. The work we've done has been under the name Free Group or the Flat Reality Earth Explorers. And some of that work is available to see in the Flatlanders series. That's the bulk of it right now. It's been very tough up to this point, to the point where I even created Flat Earth Anonymous, because it's been such a difficult nowhere path that it's been very destructive for me to be a flat earther. And I look forward to this type of work breaking out of the argument phase so we can actually understand more about where we live. I can't thank you enough.
Awesome. I'd like to thank you guys again for showing up. This was an awesome conversation. Again, you can find Beerman's paper at medicinalmass.com/science. You can find all the stuff we do at Medicinal Mass by just searching at Demon Stride on Google. Catch you guys later.